We're recording the lesson.
Oh, record. You said reward. I said
Candy? I thought 1 and 3 were really tricky. Maybe also 2? No, but so I think when it's a straightforward alternating series test is not bad. College Board just loves to do the most. So let's look at 1. Pay attention to the fact that it says Bn is this function just written as like a series instead, and being multiplied by -1 to the n. So if I took the limit of this, yeah, the numerator is like not a constant number, but the numerator is never going to be bigger than 3. And then the denominator has an x squared. So I would say that this limit is 0. But it's the whole reason they gave you the f prime and g in this graph was because figuring out if f is decreasing or not, just by looking at these numbers, by doing like 2 and then cosine n plus 1 over n plus 1 squared versus the original way that looked, is not going to be like easy for you to tell which one's bigger, because similar to like number 3, when we have a sine without like, or cosine, without like a pi making those numbers only be 1 or -1, that sign there is like, it's hard to explain if it's not really in like pi radians, but like sine of 5, I think it's in like quadrant 4. Like it's negative, but sine of 1 is in quadrant 1, right? Like think about pi over 3 pi over 2. 3 pi over 2 is like 9 divided by 2. 3 pi over 2 is like 4.5-ish. And so like sine of 5 is in quadrant 4. Sine of 6 is also in quadrant 4, but then sine of 7 is back being positive and in quadrant 1. So these trig functions are not like just being positive or -1, because they don't. This doesn't have a pi or 2 pi plus 1 over whatever number. So this is not on 2 and number 3 is not actually an alternating series, because the sine number is not actually consistently increasing or decreasing, or it's not converging by alternating series because the sine is not increasing or decreasing, making the whole thing like consistently, right? Like it's like increasing until here, and then it starts decreasing, and then it starts increasing again, and it's just not working the way that you think. Oh, I forgot, I'm like lagging like crazy here. Okay, it's not working the way that you think it should be working, I would guess. So similar over here, I can't tell if cosine is consistently increasing or decreasing. So because of that, really you could eliminate being able to do the alternating series test, but the whole reason they gave you all of this information is that the numerator of the derivative is cosine, or is g. What? Cosine. So the numerator of the derivative is this graph of g. So if we're talking about derivatives, what's significant about the derivative? What it like for figuring out if it's decreasing or increasing? What in general, what does the derivative have to be? Right, so the derivative has to be negative in order for you to say that it's decreasing. So the derivative has to be negative to claim that it's decreasing. The graph of this, even though there's a negative in front of this, okay, the negative in front would reflect this graph. And then what's significant about the bottom? Is that ever going to change any of the signs? No, so this is always positive. So yeah, the negative might have flipped that graph over, but that graph is still oscillating. So the graph is not, like g of x is not strictly positive or negative. It's oscillating. So since it's not strictly positive or negative, that means that f, because this is part, g of x is kind of part of the derivative of f, that means that f is not decreasing. So if f is not decreasing, and f is b, and b is the thing in the geometry or in the alternating series, then that means that the series can't use the alternating series test, because the function has to be, the limit has to be 0, and the function has to be decreasing. So we would have picked D as in donut. Usually, I don't want to say all the time, but like most of the time, College Board doesn't give you things just for funsies. Like they're not going to include this crazy graph just like for giggles. You know, there's a reason that they gave that to you, so you could visualize that the derivative was not only positive or negative. So just fun fact for your life. Their answers might have some distractors in it, but the like stem of the question is not usually gonna distract you as hard. Okay, now let's look at the verbiage here. Alternating series test. Does it prove divergence? No, so it's not A. All right, alternating series test. We have to do the limit. What does the limit need to equal? 0. What does this limit equal?
4.
Yes, 4, which is not 0, so it's not B. Okay, now we're between C and D. And I think it might have been hard for you to tell. This is different than what I was talking about on number 1 and 3. Do you see how there's a pi with the cosine n? So cosine pi n, if you want to expand out, plug in 1, plug in 2, plug in 3. These are only ever going to output positive and negative ones. So cosine pi n is the same thing. It's equivalent to negative 1 to the n. So this series is really negative 1 to the n plus 1 times cosine pi n. So it's like times negative 1 to the n over n squared. And we have the same base. So what are you going to do with their exponents? Same base, negative 1, negative 1. What do you do with the exponents? Add them. So you have 2n plus 1 over n squared. And then negative 1 to the 2n plus 1, what does that equal? Right, it's always an odd, which would make this number always be negative 1, which means we're not oscillating. Or alternating, I guess, since it's alternating. You can't use the alternating series test if the series is not alternating. It was like non-alternating in disguise. All right, then checking this one, the limit, it's big bottom. So does it equal 0? Yes. And on a multiple choice test, you can just like plug in 1 and then plug in 2 and then plug in 3 and see if it's getting smaller. Is it getting smaller? I think it would be, because look, the denominator is like squared, it's bigger, right? So like as we're going towards infinity, the denominator is going to be getting bigger, and it's going to be getting much bigger than the numerator. So it is also decreasing. D as in not divergent. And then, okay, on this one, I feel like the piecewise part of 3 was not helpful for me, but looking at the actual like compressed equation on 1 was easier. So is this limit of this 1 0? Yes. Is it decreasing? Yes. Okay, then I don't know if it's really the limit, it's really this sign part is not always consistently 1 or negative 1. So since this is not really like it's not really an alternating series. So it's not just negative 1 or positive 1. You're plugging in sine 1 and then like sine 2. But then when we get to sine 5 is actually smaller than sine 1. and then the denominator would be bigger, and the numerator is not consistent. It's not it's not actually an alternating series. Because that sign here would be going from some positive number, and then the next term might be positive, but then the next term might be negative, and the next term might be negative, and the next term after that might be negative. And so like it's conflicting with the signs of whether it's alternating series. So since it's not alternating, then it would not be an alternating. It's like messing up the alternating, so it can't be this one. Then, okay, the piecewise function, I looked at that and was like, I don't really know how this is going to help me figure out what's going on here. But kind of helpful to notice, though, in the piecewise series that these signs are not the same thing, which is why they had to write it as a piecewise. So the negative term, when we're adding these up, we are alternating, but it's not actually decreasing. Because look, from this term, the next term, okay, so this one's bigger than this one, right? So these two are bigger. The denominators is all I'm talking about. But then, how about this? Is this one bigger than this one? It's not, because the square root 2, oh wait. For going, wait, huh? I feel like I just said that backwards. Okay, so the bottoms, we got like 3, and then we got like 1, and then we got like 3, even 3 again, and then we got like 1-ish again, and then we got 3, and then we got 1. Like, it's not really decreasing, right? But also, if you think of like the subtracting term, you could just look at the bottoms. The subtracting term is actually bigger than the adding term, so it's not decreasing. It would be like a better way, not decreasing. You might want to like actually calculate the numbers to prove that those are not decreasing, but it's not actually a decreasing function. I don't know if my explanation was good or not, but it was not decreasing. The subtracted, this is the adding term, and this is the subtracting term. And then we're alternating signs, but like it's not actually a decreasing function. So only A. Yippee. All right, today we are doing almost our last thing. How exciting. I think the first part of today's lesson is very easy. And then the second part of today's lesson is not terribly difficult, but it is pretty important. We're going to go back to it on Thursday. I figure while we're thinking about alternating series, we should just do the rest of it. Next year, I'll make this be 3-7. All right. So absolute or conditional convergence. The thing that's like kind of annoying about alternating series is that they have this absolute versus conditional convergence situation going on. And this is kind of the only series that has this issue. So, absolute convergence. I'll change this for Graham.
Thank you.
You're welcome. So if this series, absolute convergence says if I take the absolute value of the series, so I'm ignoring the fact that it's alternating, and I'm just looking at if the series was absolute valued. If that converges, then the original alternating series converges absolutely. So because sometimes some of these alternating series are only converging because they're alternating series. If you think about the alternating harmonic series. This one, the limit of 1 over n would be big bottom, and it would be decreasing. So this would have been a converging alternating series. But when we take the absolute value of it, it's really 1 over n. What type of series test would you use here? P series. P is equal to 1, which is less than or equal to 1, so it's small. It diverges by P series. So the only reason this alternating series was converging was because it was an alternating series. It wasn't absolute value always going to be converging. So when this happens, when you are just looking at, like without the -1 part, just the absolute value of the function, if you get that it diverges, then that's a conditional convergence. So it converges conditionally because it's like, ew, you're only convergent because you're an alternating series. You're not like always convergent. So, So the absolute convergence is like you are always converging, no matter even if we didn't have the alternating part in there. The conditional conversion is like you're just, do you even go here? You diverge if it was like -1 was not involved in there. Let's try to do, and this is the only case that this happens, because it's the only one that has that negative positive thing making it be converging or not. So if you see on an AP exam, like, is this absolutely converging? Or which of the following series is absolutely convergent? Well, one, it has to be an alternating series, right? So like you're not going to pick the series that's not -1 to the whatever power. So let's figure out if it's absolutely converging, conditionally convergent, or divergent. First thing you want to do is make sure that it is at least converging by the alternating series test. So check to make sure that's converging by the alternating series test. The limit as n goes to infinity of n factorial over 2 to the n. An n factorial compared to pretty much every other type of function is going to be bigger. So we have a big top. So the factorial is greater than 2 to the n. That means this is big top, which is big top equal to 0? No. So this is not equal to 0. We are, AST is inconclusive. So maybe before we did the alternating series test, we should have used our eyeballs and done what other test? Yes. So by using our eyeballs, we see that's bigger on the top. So let's do, and the other test is going to be nth term test for divergence. You could think of this as oscillating because it has the -1, and it is oscillating. It's oscillating between positive and negative infinity because it's big top. Does that equal 0? Definitely not. So since it doesn't equal 0, what does that imply? Diverges. So just because you see that's alternating doesn't mean that the alternating series test is always going to work for it. In fact, you can like eyeball it and be like, oh, that's probably not the one I'm going to use because I see a factorial in the top. It's big top. It's definitely not going to pass the alternating series test. And just go straight into the nth term test.
On the AP exam, is there always going to be some sort of like series FRQ?
Yes. Yep. In fact, last year there was 2 series FRQs. Which I was like, rude. On B, is the nth term test for divergence going to work here? No, it's big bottom. It's probably going to be an alternating series test that will work. So remember, alternating series test has 2 parts. First, the limit of just the not alternating has to equal 0. Does it? Yeah, it's big bottom. And then we have to see if it's decreasing. 1 over the square root of n compared with, here's something that I did I think a better job in your class period than I did in second period. But make sure when you are substituting in n plus 1, you're doing it where the input variable is. You have n plus 1 should all be under the square root. It is not square root of n plus 1. Okay, so then is the denominator getting bigger? So then is the fraction getting smaller? Yes. This one's easy to tell because the numerator is not changing. It is decreasing. So because the limit's 0 and the function's decreasing, that means that -1 to the n over square root of n is converging by the alternating series test. But now we have to figure out, is it absolutely convergent or just conditionally convergent? So in order to test if it's absolutely convergent or conditionally convergent, you have to take the absolute value of the original series, which is basically looking at the part at the Bn part, like the part we've been doing the limit of and comparing if it's decreasing. So when I absolute value the -1, just kind of like, we don't care, it's just 1. What kind of series test could you use to see if this is converging or diverging? P series. So P is equal to 1/2, which is small. So that diverges. So because the absolute value diverged, then the original series is conditionally you're only convergent because you're alternating. So here's some flow charts to kind of help you remember what's going on here. I like this flow chart better personally. So like if you see this series is diverging, you just stop. And the only way, remember, you can only prove something is divergent. Well, you can't only, but you're not going to prove something's divergent with the alternating series test. So this would be like not using alternating series test to prove that's diverging. You'd be doing probably the nth term test for divergence or maybe a comparison test or something. And then convergence, this would be using alternating series test. And then if the alternating series test is convergent, then you prove that it's absolutely convergent if the absolute value converges by another test. Both of these are really like by another test. Like not the alternating series test, so P series test, geometric series test, whatever. If the absolute value diverges, then it's conditionally convergent. So try to do A, 2A. Is that always, you're trying to figure out if it's greater than? Oh, the equals to? Yeah, the equals to is just, it doesn't really matter, you can put greater than. But the equals to is kind of like the general practice that people use just in case like one of the terms is equal, like maybe the n could equal 0. Like one of them might be the same, but then as long as the majority of the time that one is smaller than that one, then it's decreasing.
I just assumed that it would be.
Okay, wait, so.
No, it didn't.
I'm not, when you do the opposite value, say that again? But when you do the opposite value for part F, it's the same thing as.
It would be 1.
Right?
The ones on what?
So it's totally.
Like the absolute value of -1 and anything is 1.
Right.
Yeah,
So
that test was
It's bigger than 1.
It did? It does?
This n squared is like n to the 1/2.
I don't know why I was like,
Yeah.
When you do the absolute value, you just get the same thing as the
Yeah, you have to do a comparison test.
That's what I was afraid of. But then I tried to do comparison, right, and do like n over n squared as a comparison. But you can't do p series for that because of the n in the top, right?
But then you can reduce them.
1 over n squared, 1.5.
So it's like n to the negative.
This Russell?
No, n to the 3.
1 over n to the 3 halves.
That's what I'm saying. 1 to the
Yeah.
or n to the negative 3 halves.
So
Okay, wait. Pause.
which direction? Which one needs to be bigger? The original or the plus one?
The bottom needs no. It needs to be decreasing. So the original needs to be high.
Okay.
Okay, so here we're comparing whether or not they're bigger. And it is really hard to compare when the numerator and the denominator are both changed. But maybe if you're like, I need to see these as, I need to see like the comparison in terms of n, not in terms of numbers. But like for your own brain power, you could plug in numbers. So like plug in like 4. So 4, and then we have, this would be 17, and this would be 26, right? So like, is 5 over 26 smaller than 4 over 17, which like, that's really like 1/4 compared to 1/5, right? So it's close, but 1/5 is definitely smaller than 1/4. Oh, you could try a couple other numbers too if you need to, but this is definitely decreasing. And Davis asked a good question about the less than equals to. The equals to is kind of like a standard convention that is sort of safeguarding if maybe like, it's not the case here, but if we had 0 or some number that you could think of to plug in the series on both n and then n plus 1, maybe they could be equal to each other like in one situation, but as long as the n plus 1 is less than n for the majority of it, then it's decreasing. So the equals to is kind of there like as like a safeguard, so that you don't think, oh shoot, this one situation that I found where they're equal to each other like breaks the fact that it's decreasing. It doesn't. So that's why the equals to is there. If you don't put an equals to, you're not gonna like lose credit. All right, so this is converging by the alternating series test. And now we're doing the absolute versus conditional. So we're looking at square root of n over n squared plus 1. That's the absolute value of it. We don't have like a special case for this, but we do have a way to evaluate it. What will we do? We can do a comparison test. So the thing I'm comparing it with is going to be square root of n over n squared, which simplifies to, that's like n to the 1/2 over n squared. So there's going to be 1 over n to the 3/2. P is 3 over 2. So it's a converging P series. We can't just say this is now absolutely converging. You have to finish the comparison test. So we're either doing the direct comparison test or we're doing the limit comparison test. I kind of feel like this case is sort of easy to look at the original thing and compare it with this one, because the original thing has a bigger bottom, so that means that it's smaller than the comparison. This comparison is larger. That converges.
That's lesser.
Yeah, it's not the original one. It's the thing you're comparing. It has to be bigger and squishing it down to be converging. So converges by direct comparison test. Now you can say then that the alternating thing absolutely converges. No. That work above was what it like showing me. You do have to show me why you're saying absolute convergence. Like this is proving the absolute convergence, but no. That's just part of the alternating series test. All right, try B. I think B should be very fast. You can almost eyeball it. Hint. So if I'm eyeballing it, what do we see happening? Big top. So what test are we using? Nth term test for divergence. I guess technically that's a K there. I get out your chart and your calculator. So it can be a Desmos calculator or a TI-84 or whatever. Get out the chart and the calculator. We're just writing a note about absolute convergence. We're just adding in a little note here for ourselves. So we have absolute convergence and conditional convergence just added in as a note for the alternating series test. Because you need to know whether it's always converging, or if it's just because it's an alternating series. A lot of the alternating series are ones that they kind of happen pretty frequently in like coding. Like we're also going to go into Taylor series, which is kind of always an alternating series, or like often an alternating series. So we need to kind of get the rules down for it. Now, I meant to delete this, so this part right here, we don't care. We're not rearranging. And we're going to do the alternating series remainder. Okay, so doing the remainder. Before, in a geometric series, I said geometric series are the only ones that we can find the sum of. And I still stand by that statement. But we're going to start to try to find more partial sums. And if you remember back to the beginning of this unit, a partial sum is like adding up to like some number, like maybe the first 5 terms, maybe the first 10 terms. That's the partial sum. So then you might get some partial sum that is really close, like a good approximate for the sum as it goes to infinity. But you could have this thing called a remainder. So let's read this statement. If you have a convergent alternating series that's decreasing, which would make it be convergent, so I don't know. Then the absolute value of the remainder involved in approximating the sum, which this is like the infinite sum, and this is your partial sum. So this is adding up like the first n terms in the series. So the absolute value of the remainder involved in approximating the sum by a partial sum is less than or equal to the first neglected term. So the first neglected term would be the first term. Like if I stopped on the 5th term, if I'm adding up the first 5 terms of the series, the first neglected term is the 6th term in the series. So it's like the next term. So your first neglected term. The thing about remainders are often also called errors. So like how close to being accurate to the actual sum were you? So you might have to add on this remainder or this error to make it actually equal the sum. So this is often called the error. So remainder, maybe error. So you might see it with like a capital E sometimes too. The error, what I think of in this formula is we're thinking margin of error. So in the margin of error formula, you take how much you want, subtract how much you actually have, and then you have some error amount that you want to be within. So like this is your error and you want it to be within some like decimal point. So say I'm manufacturing shirts and I want a medium shirt to have a shoulder width of 20 inches, but my actual shoulder width of the garment I made has 19.5 inches. If I say that I'm okay with this margin of error being within 0.5 of 20, then I would send that shirt off to market. But if I said I want that medium shirt to actually be like 0.1 inches of 20, then we'd have to like take that shirt back and redo it. I wish clothing manufacturers had smaller margins of errors for the different shirts. You know, you get one shirt that's like in red and you're like, oh, it's so cute. I'm going to go get it in blue. And then the blue like fits completely differently than the red. And you're like, what is your margin of error? Not small enough is the answer. Okay, so on example 3, when does the series provided give whatever accuracy? So we have determined the number of terms required to approximate the sum of the convergent series within 3 decimal places of accuracy is what that's telling you. So first, yes, you can confirm that this is a convergent alternating series. Is its limit equal to 1? Or 0, I mean? Yes. Is it decreasing? Yes. It's also absolutely convergent because P is bigger than 1. But that's not what it's asking us. It kind of told us it was convergent. We need to figure out how many terms. What does n determine the smallest n? So smallest value of n, that when we add up that many terms will be accurate to the infinite sum within 1/100th. So this is our remainder, basically our error. We want to figure out what first neglected term we're going to end up on. So we're like this part of the equation. This is what we're dealing with. It's absolute valued. We have 1 over, I'm plugging in n plus 1 where I see an n squared. Okay, then let's read it. We want our first neglected term to be the least error. So what way should the inequality be facing? Less than. All right, we want less than. And since I have a fraction on the left, I want to make this a fraction on the right. So what fraction is it going to be? 1 over 1,000. All right, now we have kind of a rational equation. I can cross multiply, like multiply both sides by 1 over 1,000, or sorry, just 1,000, and then multiply both sides by n plus 1 squared.
How did you get these
because this part. That's the number we want to be within. So 0.001 is 1 over 1,000. All right, I'm solving for how many terms? Noah?
Where did the negative 1 to n plus 1 go?
It was absolute valued. So it's never going to be that negative part. All right, I'm trying to figure out how many values of n. So what would I do? Square root. When we square root both sides of something, we typically, especially in inequality, have to figure out the negatives and the positives. And that would also flip the sign of the inequality. But what do we know about n? It's always positive. So I'm not even going to deal with the negative square root of 1,000. So that means that my sign doesn't have to change directions either for the negative part. It's high key bothering me that the n is on the right hand side of the inequality. Subtracting 1. All right, this is when we kind of need our calculator. Square root of 1,000 is not 10. Minus 1. You have to subtract 1 also. So 30.6227-ish. Okay, so then we want the least value of n that will make this, when we add up, have that margin of error of 0.001. So what would be the least value of n? 31. 30 is not going to be accurate. It's going to be within 0.01, not 0.001. So 30 is not far enough. So what we just found was we wanted the least value of the actual infinite thing. So we need 31 terms to represent that infinite sum to accuracy of 3 decimal places. If we went to 50 terms, we would still be accurate to 0.001. We probably have even further accuracy. But you'd have to add up the first 31 terms. Zeppelin?
So usually like round up to the next 5 number?
Yes. Yeah. So remember, n is always like whole, like integer values. This is relevant. Figuring out the error of margin of error and how many terms we need to actually be accurate is relevant, especially when we're trying to code something, to say, hey, here is this series that we're saying there's this iteration that's going on and on and on, and we know that this is accurate if we can do this 31 times versus like 3 times. So in the next part of the unit, we're going to be doing Taylor series, which Taylor series have their own error boundary, but Taylor series is how your calculator is programmed to find all the non-transcendental functions, which means like your calculator is running a Taylor series every time you use the sine button and the cosine button and the log button and e and inverse trig functions. Like your calculator is using a Taylor series. Taylor series are actually how computers run all of the things that aren't like multiply, add, subtract. So fun fact. Try to do B. This one's a little bit harder because the factorial. Excuse me? Nothing. The absolute value just gets rid of the negative 1 to the n. right, in this situation, you have a exponential function, which we could do logs to deal with that, but it's the n factorial that we really don't have an inverse operation of factorialing other than like maybe dividing by n factorial, but that's still not going to help us solve for n because it's like dividing by the thing I'm trying to solve for. So when it's not easy to solve for n, what you can do is you can try values of n. It's not like a very great, it's not super fun. It might be a little tedious, but that also kind of means you're probably going to get there faster. So think before you write anything down. If I tried n equals, bless you, 1, I'd have 4 times 2 factorial. Is that going to get you anywhere close to 1,000? No. If I try n equals 2, that'd be 8 times 6. Not close to 1,000. Let's maybe try n equals 3. This is also not big enough, but I just want you to see like the process. 1,000. 2 to the 3 plus 1 times 3 plus 1 factorial. 4 factorial is 4 times 3 times 2 times 1. So it's really like 4 times 6. Yep.
Why is there plus 1 in the exponent?
Because we're doing the next term in the series. So you're doing n plus 1. Okay, so was this the right value of n?
No.
No, we needed it to be bigger than 1,000. Let's try 4. Now we're doing 24 times 5. Is 32 times 120 bigger than 1,000? Yes. So how many terms do you need in order to get this series to be accurate to 1,000?
4.
4. Yes.
Could you plug in terms for n like for any of them? Technically? Or only?
Yeah, but like, okay, if you're trying n's over here, you'd be there for a while,
Yeah.
right? Like if you start at 3, well, maybe you'd start higher than 3, but still, like,
Yeah.
if you started there, you might be like sitting there for a minute.
Okay.
I think it's a little faster if you can solve it by hand, like if it's a square root or whatever, that's easy to deal with by hand. But like when there's like factorials involved, it's probably better to just plug in numbers.
Yeah.
Yes.
So you just plug things in until you get something greater than 1,000?
Yep.
So we have a calculator for this?
If it's no calculator, then the accuracy is probably going to be a little bit lower than 1,000, like 100 or whatever. 7.
They'll always give you the accuracy that you're solving for?
Yes, unless it's something like this one, which is a different context. Okay, so example 4, approximate the sum of the first 5 terms of the series. Write your approximate in a compound inequality to 6 decimal places. So this is kind of this one's using the s minus sn, and then less than equal to an plus 1 part. So the first part is we're expanding out the first 5 terms. This is going to give us our Sn. If we're expanding out, what n are we starting at?
1.
Okay, so starting at 1. Negative 1 to the 1 plus 1 over 3 plus 2. Okay, then plugging in 2, n equals 2, we're going to have negative 1 to the 3, so it's going to be minus. You kind of can not have to plug into the numerator anymore. You just follow the pattern. And then 6 plus 2 is 8. Nine plus 2. 12 plus 2. 1, 2, 3, 4, 5. All right, use your calculator and tell me what S5 is equal to as a fraction.
Does that mean we just
Mm-hmm. Should be a really, really big fraction.
8,260.
Correct. If you didn't do it as a fraction and you did it as a decimal, it'd be like that's as far as I think Desmo should be earlier. So I'm just gonna write as a fraction because I find that a lot easier to write than the decimal, but you do you, boo. So this is SN. We need to compare it with AN plus 1. All right, so if SN is 5, then what would AN plus 1 be? What am I plugging into the? Yes, 6. So we're really finding a 6, and it's absolute valued. So really I'm just plugging in 6 to the bottom. Okay, 6 times 3 is 18, plus 2, 20. And now we're going to put this into that inequality. I also like keeping S5 as a fraction because you don't have like rounding off issues where your decimals are going to get weird. And I don't need absolute values around 1 over 20 because I know that that's positive. And we want to solve for S. So this is going to tell us within the first 5 terms how accurate is our sum to the actual sum of this equation, of this series. When we solve absolute value inequalities, you need to have the original way that it looked, and you need to have the opposite. So remember, when you have the opposite, you're multiplying both sides of this by -1. And when we multiply both sides by -1, it flips the inequality around and it flips the sign. But then the absolute value like flings off the negative. So then when I have the sign flipped, oops, when I flip that over and write it on the left side, then it's going to be this way. And I'm just adding that crazy fraction to both sides.
Sorry for the interruption. Can you send Isabel over to the magnet office?
Okay.
Thanks.
Which now it said write it as decimal places. I think this would be 0.103304 is right number of decimal places. Less than equal to S. It's right next one. So basically, if I only use the first 5 terms to sum up this series, I would be accurate within like 0.1, which is not great. I probably need a little bit more terms to be accurate, more than like 0.1 of a decimal place. Oh, I meant to ask you, how do you think I would make this more accurate? By getting more terms. So the more terms, as n is going to infinity, it's going to be closer and closer to actually going, like as we're approaching infinity, that would make this more accurate. So the bigger the n, the more accurate your representation for the infinite series would be. All right, on your classwork, we are going to do 1 through 3, should be fast, and 9 and 12. 1 through 3, 9, 12. 1 through 3. 1 through 3. And then 9 and 12. 12. Should be lightning speed, especially 1 through 3.